Pregnancy is one of the most emotional and vulnerable experiences in a woman's life. Taking a pregnancy test should be a safe and private experience for all. However, over 20 million blind or visually impaired women do not have access to a convenient and confidential method of testing for pregnancy. Currently, VI women must rely on other people to find out whether they are expecting a child. We aim to provide them with a discreet alternative to the existing pregnancy tests, which would provide results without the need of vision.
We contacted 15 of our target users to gain insight into their preferences. Most of them would be willing to pay under £15 for the test, and all of them prefer a cab for collecting the urine. Given the fact that most of the visually impaired women agreed that an audio output is the most reliable choice, we decided to use a buzzer for our design that could be controlled by a push button to ensure privacy. A tactile alternative was implemented to make our device suitable for users who are also hearing impaired. For hygienic purposes, we decided that our design should be single-use. The respondents also did not want to rely on phones. The test results should be repeatable, of a portable size, and accurate.
This is our full design. We'll now go through each part in detail.
The pregnancy test strip used is an ordinary lateral flow strip that you can buy from a pharmacy. The user dips the end of the strip into a sample of urine and waits. On the strip, a positive result is indicated by two visible lines, one being the control line, which shows that the test has worked properly, and the other one is the test line. A negative result is represented by the control line only. An invalid result is shown when there is no control line.
This is the custom PCB we manufactured. Now we will go through each section of the PCB. The LED's light reflects off the test strip and is detected by the two phototransistor pairs that are positioned below where the indication line should appear. In the positive case, where both lines appear, the light detected is equal and so are the currents running through the phototransistors. Where no line is present, less light is absorbed by the white strip, so more light reflects. In the negative case, the second line does not appear and hence a higher current is produced through phototransistor 2. We picked this method to allow us to use the pre-existing lateral flow strip technology to keep the costs down. For testing, we soldered a small PCB containing this design and positioned it in the testing box so that the strip was facing it. The lid was closed to block out external light. The blue and red lines shown on the Arduino plotter on the right are the currents detected by the two pairs of phototransistors. Initially, the strip was in the positive position, which is why the blue and red currents are equal. When it is moved to the negative position, the pair of phototransistors that is represented in red on the plotter detects more light.
An Arduino Nano was used as the microcontroller to process the inputs from the phototransistors and send the corresponding signal to the output methods.
To meet the audio and tactile user requirement, a buzzer will produce sound and the motor will rotate the cube. The entire circuitry is powered up by a 6-volt N-type battery.
The casing consists of 4 parts: the rotating cube, the 2 halves of the main casing, and the cap which covers the testing strip. First, the motor resets to the blank face. Now it processes the result and displays the square indicating positive. The user will know to feel that side for the result as it aligns with the arrow. If the result is negative, the sunken circle will be aligned. Now we will evaluate our design. The buzzer's sound is repeated when the button is pressed. However, the current battery does not allow this yet. Our device currently is unable to detect an invalid result. It can be used entirely without assistance, but exceeds the cost target. A plastic cup will be provided to collect urine. The size is larger than planned, but it is single use as the respondents preferred.
These are our objectives for future prototype iterations. To improve functionality, future versions should be able to recognize and display an invalid result. To improve communication, the buzzer should be replaced by a pre-recorded spoken output and braille added to the shapes of the cube. Add an absorbent pill to prevent damage to circuitry by excess liquid. In terms of usability, reduce dimensions to improve portability and change the material of the cap to be more elastic for easier removal and reattachment. The cost should be reduced to under £15 by switching the manufacturing process of the casing to injection molding, for example.
We would like to finish by extending our thanks to Dr. Radcliffe and all the lab technicians for their moral and academic support.